So I am thrilled to announce that we have the Query Optimizer OG himself, Bill McKenna, who will be giving a session today on the Presto Query Optimizer. Bill is a principal engineer at Ahana, and we are thrilled to have him up here speaking. So Bill, I'll pass it over to you.
All right, thank you, Allie. Yeah, so I'm relatively new to Presto, to open source community, to Java, and so I joined 5 months ago, and we've been doing kind of a deep dive on the Presto Query Optimizer, seeing what the pluses and minuses of it are. So that's primarily what I'm going to talk to you about today, and then suggestions for the future. So I know the title of the talk was originally the future of the Presto Optimizer, but I don't control that, but I can give some suggestions for the future. Again, it'll be an introduction. I'll give a little of my background so you know the perspective I'm bringing. And I'm going to talk about overall optimizer architectures, like they fit broadly into two different camps. And then I'll try to say where some of the major optimizers fit in those two camps and where I think Presto fits. It has features of both, really. And again, yeah, current state and areas for improvement. So we're going to start kind of at a high level, and I am going to get a little bit detailed. We're going to go into a little bit of detail, and then we'll pop back out. So I'm assuming that most people know what a query optimizer was, or if you are in the audience, and you probably do know what an optimizer is, but basically it's how do you get you've got a SQL statement, you need to execute this statement. SQL is the logical description, right? And you need to get something that your execution engine can execute. So what happens in between? You wave a magic wand, and it finds the best plan for you. So how does it do that? That's kind of the magic of the optimizer. Okay, so a little bit of background about me, some boring background. Don't like to talk about myself too much. But yeah, I got my PhD in computer science, University of Colorado at Boulder. I was part of the Volcano Query Processing Project. If any of you know Gertz Graefe, I was his first PhD student. Part of my dissertation was the Volcano Query Optimizer generator, which sounds kind of cool because it actually generated an optimizer for you. Also part of my dissertation was a novel search algorithm. So query optimization is really a search problem, right? You have lots of alternatives, but at the end of the day, it's a search through a large space of alternatives. So you have logical alternatives. Join ABC is equivalent to join BCA, whatever. Each one of those has multiple physical implementations. So you have to look through that space, and it's quite a large space. So this is an NP-hard problem, right? For star-shaped schemas, which probably what most of us are using, it's exponential complexity. And so you have to look through that space effectively and efficiently. From there, I was an assistant professor in computer science in New Zealand. Then I went to Bell Labs and did some work in the database research department there. And it was on extensible optimization frameworks. So I've worked at query optimizers at Redbrick. If anybody, I know at least one person knows what Redbrick was. So it was a database geared toward optimizing for star schemas. Also worked at Oracle. Did 2 stints at Teradata. Worked at Parexel, which became Amazon Redshift. They purchased the technology from us, the code line. Let's see, Salesforce, I worked at Salesforce and ServiceNow, and now I'm at Ahana. Some of the more interesting projects, I think, that I had an opportunity to work on. So I rewrote the query rewrite subsystem for Teradata, and we also did Teradata has a new architecture that's it's a hybrid cloud on-prem architecture. So they needed a global optimizer for that. So my latest stint at Teradata, I worked on that. Super interesting project was the to architect and develop pair Excel's query optimizer. So this was a greenfield effort. We started with nothing. And it was about 25 person years of effort, 5 people, 5 years. And that's what became Amazon Redshifts optimizer. They've probably changed it since then. Work at Salesforce DB, they wanted to get out from under Oracle as their database. They wanted to have their own database. So it's Postgres based, but their whole architecture really relies on the communication between the application, the Salesforce app, and the database. And every query they sent is hinted for Oracle. So now when they went to this new database, they needed a hint language. Postgres doesn't like hints, so we had to write a hint. I call it a constraint language because it's not a hint. It tells the database what to do. So there are various reasons Salesforce needed that. But that was an interesting project I worked on there. Two major, I would break optimizers into 2 main architectures. We have some IBM folks here. We were just talking about System R. So I'll call it like the System R style optimizer, which is really what DB2, Teradata, Postgres, you look at any of their codes, Salesforce DB, it's really kind of based on this. This was the seminal work in query optimization. So if you want to understand query optimization, go back to the System R paper and start there. Usually it breaks the system, breaks the optimization process into 2 pieces. Query rewrite, which is generally a heuristic, mostly heuristic, and I'll talk a little bit more about that, rules. And examples are, can I turn outer joins to inner joins? You usually don't cost that because that's a good idea, right? Predicate push down, you don't figure out every place in the tree you could possibly paste a predicate. You usually just pick it up, move it as far down as you can. You don't cost it. Inferring new predicates, usually just infer them. I have A equals B, A equals 1. Just infer B equals 1. I don't really need to do that in a cost-based way. And after that, so I always think of those as like SQL to SQL kind of rewrites. And after that rewriting is done, and the query rewrite systems themselves are architected differently. And after that's done, then you have the physical planner. So that's how you map the logical structures to the physical and come up with a plan. The way that System R does it is it does a bottom-up enumeration. So it starts with each table, figures out the access methods for each table, and then it starts building the 2-way joins, the 3-way joins, the 4-way joins. It builds them up. But what was really cool, so that's all kind of intuitive. What was really cool about System R is it has this idea of interesting physical properties. So what is an interesting physical property? In the original paper, I think the only interesting property was, what is this sorted on? So if I do a merge join on A equals B, I know that it's going to come out sorted on A. If I do a hash join, not true. So for the same join, you can get 2 physical representations. You get 2 physical implementations of that, but one is interesting if you're interested in a sort order. The other one is interested if you don't care about the sort order, right? Or, right, potentially the hash join would be interested. And yeah, very cool idea, very, similar work, as I said. Then the second major architecture was Volcano and Cascades. SQL Server, I think, if someone can correct me if I'm wrong, but I think it's pretty much a Cascades-based optimizer, at least it used to be. Apache Calcite, another Volcano Cascades-based optimizer. And this is different in the sense that what you do is what comes into the optimizer is a logical algebra representation of the input query, and then you have rules that operate on this. So you have 2 types of rules. You have logical rules, which logically transform things. So I showed a join associativity rule here. That's a logical transformation. And then you have physical implementation rules. The way Volcano drives the process is it has these complete trees that it transforms, but it drives the optimization with interesting properties top down. It doesn't do it bottom up. So a node says to its children, hey, if I'm a merge join, I would like you sorted on A. It doesn't care how it does it. It says to the other child, I'd like you sorted on B. Doesn't care how it does it. Gets back the cheapest way, and that's the way that these style optimizers work. The way that you apply these rules, you interleave these things in different ways. It uses an interesting structure. I guess it's interesting. This is part of my dissertation was the memo data structure. You guys probably see this in the Presto code. There's heavy use of this structure called memo. And if anyone here speaks Spanish, they'll get the joke. I won't go through the whole story of why I chose memo. If you're a Spanish speaker, you'll understand. And it's really a structure that implements dynamic programming. And it also was one of its properties was it's the minimum number of nodes that you need to represent a join space. It's a guaranteed minimum. It agrees with what Guy Lohmann and Ono published about the number of feasible joins. That's the minimum number of joins you need to visit or you need to construct. So memo guarantees you that. So that's the volcano cascades. And everything on this slide I'm going to talk about is what we did at ParAccel. So ParAccel was a hybrid. We looked at the best of both worlds. And I think that the System R is really quite good at enumerating the join space. It's really quite fast. What I saw is the rule-based approaches to enumerate the join space, kind of slow. My own, from years ago, that was. So what we did is we combined System R with the volcano top-down algorithm, and that was the basis for the ParAccel optimizer. Some kind of cool things we did there, and I'm going to talk about the large number of joins problem, because I think that's a problem in Presto. If you have large number of tables. So what happens when you get 128 tables in a block, right? Most of us don't think about that many tables, but it does happen. You can get 128. While I was at Teradata, they upped the number of table limit per block from 64 to 128, just because customers were asking for it. So how do you optimize a 128-way join? Interesting problem. We did a lot of work around that, and we showed that you can, we could plan a 1,000-way join pretty quickly. It's obviously heuristics, right? There's some heuristics around this, ways to decompose the join graph. It was a challenging problem. And again, yeah, it's sort of a hybrid between System R and volcano or cascades. ParAccel, I just thought about this when I was talking to my friend here in the front row about plug-and-play optimizers. We wrote all of ParAccel. This optimizer was plug-and-play. So you could pull it out and plug it into a different system. And as long as you got the input in the form that it expected, and it was going to give you a physical plan at the end, which you would have to translate to whatever your execution engine expected. And unfortunately, that's not in open source. Only two people have this, I guess, Redshift and Actian Corporation, who ended up acquiring ParAccel. Presto, again, this is what my perspective on Presto. There are a lot of instances. In Presto, the optimizer, it's not really one optimizer. You have many optimizers. And I think at last count, there are 90 optimizer instances. And it goes through these optimizer instances. Each one of them owns a set of rules. So the optimizer executes its set of rules, and then it goes and gets the next optimizer, and it executes them. So I guess I question, do you really need 90 of these things? Or that was one future direction, is maybe we can consolidate and simplify these things. It's also a little inconsistent about the way that it applies the rules. Some rules are applied using what's called an iterative optimizer. So it applies a rule, it sees if it makes progress, it applies another, it sees if it makes progress, so forth. That's the iterative model. Some of the optimizations are applied using visitors, the visitor kind of paradigm, where you visit nodes. And I believe, from when I'm talking to some folks at Meta, there's the approved way, the approved method going forward is to use iterative optimizers and not use visitors. But if anyone knows differently, they can certainly chime in. It has a reasonably complete set of decorrelation rules. So decorrelating subqueries, tough subject, and takes a lot of time to get it right. For the common cases that I've tried, it does a good job. It does a good job, It's well thought through. I'm not saying that there aren't improvements, but there are some patterns that it doesn't support. It will just throw up its hands and say something like, I don't know what to do, or it's probably a little more technical than that. But that's okay. These are complex patterns. These were things we saw at Teradata, and unlikely to see them, or you won't see them very often. The other oddity I think about it's a collection of optimizers and rules, and in ParaXL and Teradata, those rules are heuristic rules. They're heuristic rewrite rules. It doesn't matter the order that you apply these in. You could jumble them and apply them in any order. So you can do view folding, predicate inferencing, predicate pushdown, and they run in a loop. So you run it n number of times, and the magic number for n is 2, and I won't go into why it's 2, but I mean, potentially, you could put them in any order. I think there is an optimal order. In Presto, if you look at the code, you'll see this has to be run after this, right? Like this cannot be run after that, which is it's awkward because you have to keep track of these things. You have to read comments in the code. And well, why is that the case? Maybe that's another area that bears looking at. Now I'm going to drill down on one rule in particular. It's called the reorder join rules, because this is the thing that looks through the join space. This is the thing that enumerates the logical join space and maps it to physical, although it's a little odd because I said one join method, there are really two. There's, of course, cross join, because you can't get by without cross join. So there's a Cartesian product cross join, and there's a hash join, and there's really only one access method. Don't have to worry about, makes the job of the optimizer easier, because you don't have to worry about indexes. But merge join is coming down, is going to be with us soon, and I'm going to talk about some of the, well, hopefully it's going to be soon. I'm going to talk about some of the problems that the current architecture would have with things like merge join. It does a bottom-up enumeration sort of like SystemR, but the way SystemR works, it picks two tables, and it says, hey, do I have a predicate between these? Yes, I do. Okay, that's a two-way join, right? The next pair, do I have a predicate? No. Let me go to the next pair. Modulo some, issues around Cartesian products, right? Like sometimes Cartesian products are good. You have a fact table, 2 dimensions. Sometimes it's good to cross-product those guys and then join to the fact table. But what it does is builds the power set, the set of all subsets, and then it says, oh, are these guys joinable? So it goes through every one of those things and tries to see if they're joinable. The other thing where it differs is it does not handle outer join reordering, and it doesn't reorder inner joins with outer joins, or outer joins with each other, which is odd, because then outer joins become a barrier, an optimization barrier. Everything below you can do in this manner, everything above you can do in this manner, but it doesn't, your tables don't migrate across those boundaries. That's a limitation that we should lift. It's not that hard to lift. It also, I call it a poor man's memo, because when I look at it, there's only ever one logical representation that it keeps around at a time. If you find another plan that you think is better, it kicks this guy out. So it's not like System R that it keeps multiple physical plans, that have interesting properties. That's totally gone. It's totally not there. And we've talked about, how can we add that? There are two. It only optimizes for only one physical. Only one interesting property. It's distribution of the rows. So you either distribute things or you replicate them. It's the only physical property it looks at. It says, hey, the cheapest way to do this is distribute this, distribute this. It's cheaper than, replicating one. I'm done. It never looks at that one again. So it always looks at these four alternatives. It only keeps one and it goes on. Oops. The other thing I noticed was if you have a large number of tables, which I was talking about earlier, what do you do? So it does something. And I thought, well, what happens when it gets a lot of tables in there? So what it does is it chunks these things. These are configurable size chunks. It does planning within those chunks and then between the chunks. I don't think they're called chunks, but groups or whatever they're called. But how does it do that? It depends on the order, the way that you write the way that you write the from clause. If you write the from clause differently, you'll get a different plan, which is not a desirable property for the optimizer, to say the least. So I tried a query where I wrote, I have one fact table, 11 dimensions. I wrote it that way, then I wrote it the other way, and I got a different plan. That's something we should look at, and in more general terms, the entire join planning algorithm, I think, should be improved. Outer joins, and I'm going to come back to this. If you do any work, you'll see this project node all over the place. And this is also a boundary for optimization. It's very odd that sometimes you see 4, and Dave Simon even said 6, of these project nodes stuck on top of each other, stacked, and I don't really know why. I don't really know what the reasoning behind that is, because there's a rule in Postgres to add them, but then there's a rule to take them out. And so it seems like it's constantly adding these things and taking them out. But it's just like outer join. It creates a barrier for optimization. And this is one of the earliest things we noticed when we were trying to analyze plans. Like, why? That's awfully small join space. Oh, it's because of this. Join planning again, yeah. What I just said about the search space. I think better planning for large number of tables, a general way to handle physical properties in a general way, so sorting and distribution. Because if you have a merge join, you're interested in this can be partitioned by this and sorted by this, right? Or partitioned by this and not sorted. So making sorting and distribution first-class properties that are handled in a general way. There's also a rule called add exchanges, which the join ordering does some selection of whether you're going to do partitioning or replication. I shouldn't say partitioning becomes confusing if you're talking about Presto, because that can mean partitioning files. But I'm talking about partitioning, hash partitioning across nodes in the cluster. It's sort of a split brain where the reorder join rule makes some decisions, but then it can be overridden by the add exchanges. So it's kind of this, like I said, split brain that I think should be unified. Outer join reordering, again, yeah, it's kind of an important rule that you can push joins into, into outer join inputs. And I have yet to look at really the efficiency and the memory usage, because I've never seen an optimizer. I haven't worked on DB2. Sorry, I don't. but that where it's not a concern, right? Like how much memory are you consuming? And I'm looking at the code, and I guess maybe the garbage collection is super fast or something, but it looks like memory's free because there's, allocations all over the place. And, as a C++ guy, I'm always, makes me a little nervous, like what happened to that? Yeah, how fast can it plan? It seems to plan, reasonable amount of time. And again, for our 1,000-way join in Paracel, we could break that up and optimize it in about 8.5 seconds. And it's very memory, we focused on making it very memory, very stingy. This is a big one. I just ran across this one. There's most of the metadata stores, and certainly they don't really maintain key information. Like some do, some don't. I'm not an expert on the different backing stores, but at least in the code, it doesn't leverage any information about. First of all, it doesn't have in a lot of cases, you don't have foreign key, primary key information. You don't even have primary key information. So then what happens when you're doing a fact table and you're joining it to a dimension, and you're joining on two foreign keys and two primary keys? The way that the selectivity estimation works, you can actually come up with an estimate that the number of rows from joining that fact to that dimension is greater than the number of rows in the fact table, which is confusing, right? Because that's not the way it should work. Fact join to min should always be a reducing join, not an expanding join. But the consequence of the way the join selectivity estimation works, you can get more rows. We need to fix that, know how to fix it, need some information about keys. We've, on the other, and there are different ways to approach this, right? Make equals Honda, model equals Civic, like classic problem, right? What's the selectivity of those predicates? It's not selectivity 1 times selectivity 2. It's they're completely correlated. And we have some ways, we have some ideas that we're kicking around on how to do this and to solve these difficult estimation problems like that. Improving decorrelation, noticed in some of the TPCDS, it's sticking in outer joins, and it doesn't need to stick them in. They can be inner joins. So that's limiting the search space. Know how to fix some of those. Common subexpressions, I think this would be huge to tackle this. Paracel, we did that. We had exploiting common subexpressions. So if I see join ABC here and I see join ABC here, do I need to compute that twice, or can I just compute it once and reuse it? We had this is like the poster child for that. TPCH, I think it's Q15. It has revenue 0, a view, referenced twice. For example, in Teradata, it will look at that and it'll run it once and spool it and replace the view in the query with the reference to that. We saw a query, it was a query from Goldman Sachs when I was at Paracel. It was 25,000 lines. It was a single SQL statement, 25,000 lines, and it had loads of common joins in it. Loads and loads and loads of these things. And we were able to take the 25,000 lines and get it down to 2,500 using common subexpression, common subexpression factoring, or CTEs, if you will. Something else we feel like we would like is cost-based rewrites. So some rewrites are things like, if I have a union of two fact table fragments, I join that to a dimension table. In some cases, well, you can push that, you can do the join twice, right? You could do it on each fragment, then do the union. You could do the union, then join. And in order to do that really in the right way, you need to cost those things. And the only thing that's costed in Presto right now is when you're doing this join space, right? None of the other rewrites are costed as far as I know. Yeah, understanding and traceability. This was something when I came, I've done this a few times at different places. What is the optimizer doing, right? Like I've got a 10-way join. I don't know what it's doing. Why is it picking this? Why is it not picking that? And we've developed a prototype for this. We'll propose it to the community. We'll propose it to the open source community, see what they think, see if they like it. I'll show an example of it in a minute. I'm running out of time. But it traces all the decisions the optimizer makes. So if you want to know why hash join AB was chosen over hash join BA, you can find it, see the comparison. It will give you the reason. The other kind of cool thing is if you want to know why one particular application of a rule happened and you want to step through it in the debugger, if you put a breakpoint, maybe that function's called 5,000 times. You don't want to stop on every call and try to, but what the trace gives you is it associates a unique ID with every call to that function. So you can say, that's the call I'm interested in. Just stop on when that unique identifier is spit out. And we also have a pretty cool, this is part of the trace facility. It is a constraint language because what we wanted to do was, this join is coming out cheaper. Why did it? I don't believe that, right? I don't believe it. I want to pick another join and really run it, because I know this guy has lower estimated cost, but it doesn't make any sense to me. So this is a little sample of a language that lets you force different join and partitioning strategies. This means replication, partitioned, and these nested. So this says join T1 to T2, replicate T2, then join to T3 and partition both and then join them together. And this is an alternative. And the trace also shows every enumerated join, why some joins won, why some lost. I don't like walking through the debugger that much. We also have very cool, so we were looking at TPCDS, right, 104 queries. You run them, you capture plans, right? You make some changes to the optimizer. Oh, what happened? How did that change my plans? Do I step through 104 of these things and say, oh, this one changed, let me look at the next one. We have an automated way to do that. So it's just, takes plan one, plan two. It's like a plan diffing tool, but it's very cool because it reports, what the differences are and where they appear in the tree. I already said something about the number of optimizers and complexity, maybe looking at machine learning for query optimization. I know that people have talked about that. Can and should we interleave optimization and execution? Teradata does something very cool. They get a plan, the optimizer gives you a plan, starts running it, maybe it does one or two joins, and then it reevaluates where it is. And it says, oh, I thought there were 1,000 rows that were going to come out. There were really 1 million. Oops. So it says, okay, let's hold up. It goes back to the optimizer and says, hey, I just learned something. There are 1 million rows, not 1,000. And it actually replans, but it keeps those intermediate results, holds them on disk, comes back with a new plan, rinse and repeat. And it just steps through this thing. Very cool. It's called IPE, Incremental Planning and Execution. I'm thinking maybe we can do something with more runtime optimization. Redbrick was interesting in that it did not have a cost-based optimizer. We built in your plans were you can think of them as a decision tree, and it made decisions at runtime based on what it's already seen. But you built the decision tree, and then it evaluated what it's seen and which plans it could choose, it should choose. It's a little snippet. I just thought I'd show a little snippet, maybe get you guys interested in. So the tracing, I can't show the whole thing, but this just gives you an idea. So the begins mark the beginning of some block that you're interested in. Usually it's a function call, but it can be a block, you know. And when you put in an end, right, it gets these begin-end pairs. So that's how it does the indentation. And there's just a whole lot of information in there that it dumps out. We use it all the time. And as I said, if you're debugging the join planning, in this case you'll see many more joins, but in this case you'll see the first two joins it tried, and it tells you which got accepted and which were pruned and why they were pruned. So they can be pruned for cost reasons, they could be pruned because you had a constraint, and yeah. All right, quick summary in my 4.5 minutes. I think the Presto framework is pretty extensible. You can add new rules. It does a pretty good job. You know, it's not like, oh my God, we have to rewrite this whole thing. But I think there are significant improvements that we've identified, and we're going to pursue those at Ahana in conjunction with the open source community, of course, because it's an open source project. And shameless recruiting plug, we are hiring, and there's Ethan is our director of engineering. And also feel free to connect with me on LinkedIn, Bill McKenna, Ahana, you'll find me on LinkedIn. We'd love to hear from you guys, get feedback, comments, and yeah. Questions, comments? Almost out of time.
So in order to create a good plan, you have to have good statistics.
Yep.
In Presto storage with iceberg tables, Hootie tables, Delta tables, do you think you have enough statistics in those?
Not right now.
So which ones do you miss the most?
Well, I mean, histograms, right? We don't have histograms because that's sort of, Dave Simon is our, you guys, if you guys were at IBM, you know Dave. So we talk, you're laughing, but yeah, Dave and I have talked, and there's certain things that we call block and tackle, right? Like block, you got to learn to block and tackle if you're going to play football. It's basic stuff, and you know, histograms to me that's block and tackle stuff. So you know, right now you have max, min, and you have number of distinct values. That's not going to get you where you need to be. Yeah, so good point. And
are you trying to get histograms into iceberg?
Me personally, I haven't. I'm not trying, but I think that, you know, there's a lot of talk about that, trying to get histograms, and it's a great project for somebody if you want to. You want to? I saw you. Did you raise your hand and volunteer for that? So yeah, that's kind of a basic thing that's missing. Yeah. Anything else? Oh.
First of all, great technical talk. So you have been with the various organizations, ServiceNow, Salesforce, Teradata.
Yeah.
And there are two things I could gather from your talk, that either for the query optimization, there are two things when you query rewrite.
There's two styles. Yeah.
And the second is the physical planner, right?
Mm-hmm.
So which one you think that is the best output?
Which of the two types of optimizers?
I mean, I have to optimize my query, where I should focus more, and that would give me the best bang for my buck.
You kind of need both, right?
Okay.
You kind of need both. It's hard.
Yeah, that's what my question. So there's no first or second.
No, I don't think so. I don't think there are any shortcuts. There's no first or second. No.
Okay.
There's someone once said, if you want to build a query optimizer, you're going to spend 7 years doing it.
Okay.
That's a hard and fast rule, and you're no exception from the rule, right? That's what this person said, and I believe that.
I see. Yeah, thanks. My second question is about your, a lot of, you use that word memo, and I don't know whether it is coming from Spanish or whether you meant from the memoization.
You want to know the story?
No, I just want to confirm because I was assuming it's memoization because you are using
Okay, it is memoization, right? Not memorization, but memoization. You
Yeah.
jot down a memo, like
Right.
you make a memo, and if you've already solved a problem, you don't go back and solve it again. So that's the memoization.
Yeah.
So one member of my PhD committee was from Mexico, and I sort of named it that because I was taking Spanish at the time as part of my PhD requirement.
Okay.
And Guillermo, of course, is William, and Bill in Spanish is Memo. So it's M-E-M-O. That's Bill in Spanish.
Oh.
So that was kind of my joke. He's the only guy that got it, but
I see.
anyway.
Yeah, but my question was totally orthogonal to it. I was thinking if we are using dynamic programming,
Yeah.
you're assuming that there's some sort of recursion in your
Yep.
query, right?
Yep.
Otherwise, you cannot.
No,
do
not,
it.
what do you mean recursion?
Because you cannot memorize.
Oh, that you're going to visit the same node more than once, right?
Yeah.
Yes, yes, you
Right.
do. Yeah.
So if my use case is not like that, whether I'm not going table by recursion, I cannot do that, right?
No,
Is it my assumption is correct?
no, you,
Because in my computer science 101, I see dynamic programming is applied where the recursion is, because you just want to memorize those things in the recursion tree, right? But my other mind says your queries are not like that always, you know.
okay, so the way the memo comes in, so suppose I've figured out the best way to do join AB partitioned by X, right? I've figured that out.
Okay.
And now I've got join AB, I could join it to C, and that might be interested for that join order. And also I could join it to D, right?
I see.
But once I've solved that subproblem, like I don't ever want to solve it again, right? Like I know that join AB partitioned by X, I have the solution. I don't need to solve it again. So that's the real idea behind dynamic programming.
Okay.
Yep.
Got it. Yeah. Okay. Thank you.
So regarding extension to his question, like what statistics should we store to make better plans? So we tried with histograms. We had T-digest and all other histograms, and we saw that we didn't have enough information about correlated columns, for example, in join. So do you know of any systems which use existing join information, like runtime information, and that can use in the memo for the new plan?
So there's the whole, I think, history-based optimization at Meta, which I don't know that much about, looking at past executions.
Yeah.
And I will tell you briefly that at Oracle, it does have a feature that's called dynamic sampling. So you come in, you see a condition like make equals Honda model equals Civic, and in certain cases, it actually goes down and reads some rows from disk. It actually reads n number of blocks. It constructs a query, it evaluates the predicate against that, and says, oh, hey, the selectivity looks like, 10%. So I'm going to assume that for the entire table, that's the population, which is kind of a cool idea.
But can you use this to store in memo, for example, for this tree, for this set of plant trees?
You could interact with Memo and store that, yeah. Yeah. Okay, I think we're over time. Okay, thank you.